So this video is to give an introduction to the NIDAC and the LabVIEW equipment on your computer. The first part will be about the NIDAC, which is a software on your computer that can measure electrical phenomena such as your voltage, current. It has a lot of applications you can use, and it's similar to multi-sim in a way. First, you can start by opening it on your computer. So we've first searched Elvis. Since then, we've clicked on digital multimeter. And we're going to use this to first test that our NIDAC even works properly. So you can start by, so you can first start by connecting your NIDAC to the computer. This will give the NIDAC power to complete your circuit. You can see the blue light glowing. So there's two probes and there's three inputs. The black one goes straight into the black one, and the probe to the left could be used to measure voltage, and on the right it would be used to measure current. It's marked by a V and A easily. Before we even start using the NIDAC for our circuit, we'll check to see. Right, so first we'll check to make sure that the fuse is not blown in the NIDAC, and you can do this by plugging both probes into the red outlets, the voltage and the current. From there, we will touch the tips of the probe together once we've already hit run on our computer, and you can do so like this. And if there is a resistance, we know it's not blown. If your multimeter read that it is over like that, then you would have to look further to see if your fuse is blown or not. So the first part of part B calls for you to grab 4 resistors, and to double check that these resistors are reading what they're stated as, you can measure it using your NIDAC. It'll be displayed on the screen. So you'll already have hit run, and you can see that this resistor is 3.55 kilo ohms. That one's closely matched to our 3.6 kilo ohm resistor that we were already asked to grab. We'll test another resistor. And we can see this one is somewhere around the 5.6 resistor, so we can assume that that is what that one is. Our third resistor measures around the 12 kilo ohms, so we can be certain that that's what the resistance of that one is. And the last resistor measures out around 33 kilo ohms. So the next part, we are going to open LabVIEW. LabVIEW is a graphical program approach that helps you visualize every aspect of your application. This is just going to further help you analyze your circuit. So the VI in LabVIEW stands for virtual instrument. Each VI has 3 components: a block diagram, a front panel, and a connector pane. We're going to talk about the front panel and the block diagram. The front panel is built using controls and indicators. Controls are inputs. They allow the user to display information to the VI. Indicators are outputs. They indicate or display the result based on the inputs given to the VI. The back panel, or the block diagram, contains the graphical source code. All of the objects placed on the front panel will appear on the back panel as terminals. The back panel also contains structures and functions which perform operations on controls and supply data to indicators. Alright, so now we're going to set up a circuit and create a power source using LabVIEW. To do this, we're going to open a blank VI in LabVIEW. And on the block diagram, you're going to right click. You can scroll down to Express. From there, you'll select Output, and then you will select DAC Assist. and you can just place this on your block diagram. Now a screen will pop up and you'll click Generate Signals, Analog Output, Voltage, and you'll select A00, and you can hit Finish. And now this next screen will pop up, and where it says Generate Signals, we're going to scroll to one sample on demand, and you can hit OK from there. Now a number voltage control needs to be hooked up to the DAC Assist. To do so, right-click on the front panel, click Number Controls, scroll down to Express, then over to Number Controls, and again onto Number Controls. And you can place this on the front panel. All right, and you're gonna connect your wire from your numeric to your data input. Okay, and now we're gonna wire our circuit. 6 on how it should be wired, but since we select our input as A00, you can start your wire there to the breadboard, and then another wire from the A ground. And then you can place your resistor between the two wires. All right, now on my DAC, we'll vary our voltage. It's going to be in increments of 2 from 0 to 12. And we'll measure the voltage across the resistor and the current through the resistor. So we're going to start by running LabVIEW. And from there, we'll place the probes in parallel with the resistor. Right? And now we'll increase our voltage to 2. And we can see we have a reading of 1.9 volts, 2.1 right in there. Next, we're going to switch and measure current. So first you'll start by switching your probes over. And current has to be measured in series, so you'll use the probes to complete the circuit in series. It's done so like this. Make sure you switch over your multimeter to amps, and it also shows you the ports where you should be plugged into. And you can change your range to better see your reading. And we see about 0.56 milliamps. All right, we'll now increase the voltage to 4 and go back to measuring in parallel. Switching your probes over to the correct spots. Right, and measuring in parallel, and we see a reading of 4 volts. We'll do current again, so we'll switch our placement on the breadboard, switch our probe over to the amps, and we'll change our multimeter to read in amps. Change the range if we need to. And we get a reading of 1.12 milliamps. We're going to increase our voltage again by 2 volts to have 6. Switch back to measure, we'll stay and measure current. So we see 1.68 milliamps, and again, that's measuring in series with the breadboard. Okay, and now we'll switch and do our voltage. So we'll switch this, switch the probes back. And we can see from reading across the resistor, we get a reading of 6.0 volts. All right, and now we'll increase the voltage to 8. And we see a reading of 7.8 volts. We're still measuring the same way, parallel across the resistor. And now we'll switch and see what the current reads. All right, we switch our multimeter over to amps and our range. We see 2.18 milliamps about. All right, now we'll increase the voltage to 10. And we'll measure our in parallel, switch the probes over. And we can see another reading of 7.8 volts. This we notice because the NIDAC limits the current to increase any further, therefore limiting the voltage to 7.8 volts. This is something you'll notice when you have a lower resistance. As you use the other resistors, you won't notice the same things. It won't top off at a certain voltage.
Yeah.
All right, so we're gonna start by using our 5.6 kilo ohm resistor, and we are first gonna measure the voltage. You can see how the circuit's set up similar to the last one, actually exactly the same as the last one. And up here, we'll change the voltage input to 2. And we can see we get a voltage reading of 1.9 volts. Next, we'll switch our wiring over to measure in series your current. And we'll switch the multimeter over to amps. And we see 0.36 milliamps for our current. All right, now we're gonna increase the voltage given again by 4, and we've kept our wiring the same on the breadboard, placement the same. And we can see the current reads 0.72 milliamps. We'll switch over and do our voltage. And we see a reading of 4.0 volts. We'll increase the voltage given to 6 now, and still keeping the same breadboard setup, we'll see another measurement of 6.0 volts. Next, we'll switch and do current. And we see a reading of 1.08 milliamps for our current. We'll increase the voltage given to 8 and leave our probes in the same spot on the breadboard, and see our current increases to 1.44 milliamps. Next, we'll switch over and measure the voltage at 8 volts given. And we see a reading of 8 volts. We'll increase our voltage to 10 volts and keep our probes the same on the breadboard, and we'll see a reading of 10 volts. Next, we'll switch over and do the current for this one. And we get a reading of 1.8 milliamps. For the 5.6 kilo ohm resistor, we notice that the voltage does not stop at 7.8 volts. It can keep increasing each time you increase the given. This is due to the current being less than 2.3 milliamps, and there will not be a limit on the voltage. You can repeat these steps for the last 2 resistors you have, and then